which is the sum of the different, let's see, it's the sum of the squares of the distances. I don't know why this turned into that. And I'm going to divide it by n minus 1. Now we're going to have an extended conversation about this n minus 1. But think of n minus 1 as being, what's the best way to describe this? It's a way to tweak the fact that we know we're not going to have as much variation in a sample as we would in a population. And we want this S to be somewhat representative of the population, which would be a group of all kids, let's say gifted kids, and the number of their siblings. All right? So this number that we're going to get when we take 40.4 divided by n minus 1 is actually the average of the squares of the distances from the data values to the mean. All right? So if I take, this is, let's go down here, this is 40.4 divided by 14, which I get 2.88, let's see, 2.886. As a rule, I like to round out to thousandths. It's just a good idea. If your data, like in this case, it's kind of crazy because your data is in discrete values. In other words, you can't have a third of a brother or a sister. That'd just be weird. But keep it out to thousandths. Keep it safe. You can usually go, if you're going to round, like if we're in whole numbers, then you round to tenths when you do standard deviations. Okay? Now, that's a good rule of thumb. But if you're just going like, Ripley, what should I round to? Go to thousandths. You'll be a better person for it. Now, I actually haven't included everything in this yet. All right? What we need to do, now think about this. The standard deviation is the average distance, so the units need to be preserved. It's the average number of kids away from the mean that our sample is. And remember, this number right here actually gave us kids squared. So this number right here is actually kids squared. So what I need to do is I need to get back to the original units that we had. Okay? We need to get back to the original units that we had. By the way, there's construction going on at the Davidson Academy right now, so if you hear some crazy sounds, some pounding, that's what you're going to hear. Okay? So you take, once you take the square root of that, what you get is 1.69, I'm going to go 9. Okay? And this is in the same units as our data. Now, there's a formula, and I'm sure you're going to want the formula. The formula is the square root of the sum of x minus x bar, the mean, squared, divided by n minus 1. And I know that this n minus 1 is going to bug you guys, but you got to bear with me just a little bit on that one. Now, that said, let's change colors. I'm going to give you the formula for sigma, which is, I'll show you here, sigma is exactly what you would expect. Now, remember, sigma is population, which means if we described this 15 data value set or sample as the actual population of, I don't know, a classroom with 15 kids, and we're defining that exclusively as a population, then everything changes. Well, everything doesn't change. One thing changes. It's the exact same formula, except it's the sum of x minus x bar squared divided by capital N. And remember, capital N, that square root, by the way, goes all the way to the bottom. Capital N is the number in the population. Now, just to plant a little seed, and hopefully it will grow to fruition, remember, a sample, in theory, is not going to have as much variation as a set. And you may look at our data and say, well, Ripley, I know people that have 5 brothers, and I know people that have 4 brothers, and I know people that have 6 brothers, and our set didn't account for it. Well, assuming that our set is randomly created, that's absolutely correct. It appears that our sample is missing some variation away from this mean. Now, clearly, if I had 5s and 6s, etc., this mean would be different. But we account for that. We cheat just a little bit by dividing by n minus 1. That's how we do it. That kind of, it balloons up. It adjusts the standard deviation, the sample standard deviation, to be more accurate. Now, it also has to do with something called degrees of freedom, which we will talk about over and over in the class. Okay? But bear with me for now. For right now, all that you're doing is you're going to study you're just going to study this formula and be able to use it on a very small sample set, or on a very small sample. If I give you an exam, I might give you 5 data values and say, Assuming that it's a sample, find the standard deviation. Assuming that it's a population, find the standard deviation. Okay? Hopefully this was helpful. Again, I'm going to show you on the calculator how to do all of this so you can always check your work, which I think is very important. Thanks for your attention. We'll move on to the next topic.